Did you guys get the chance to think about midterm 3 by any chance? Efficiently, like we
For the date.
yeah, date. Not it.
No,
Yeah.
not really.
So will you guys think about it?
Yeah, within 2 or 3 days.
Tell it again.
Hopefully within 2 or 3 days.
That's right. It's okay. So how about this? I think just to make you guys work on it. So there's homework 8, of course. That's I think due tomorrow. That should be. We have already covered stuff for this. I just want to give a quantum mechanical interpretation of the whole thing. So that's tomorrow. Midterm 3. By default, unless you guys tell me, it's going to be November. How does this work? So 9, 10, 11, 12, 12 plus 7, 9.
18. We decided for 18.
10,
Yeah, 18 is Thursday before we leave. So.
12 plus 7.
19.
Is it? Thursday, right?
That's Thursday.
Is today now or tomorrow is November 9? You have 11 plus 7. Yeah. Yes, I thought I think some of you guys wanted to change it, right? So feel free to change it, but if you guys don't change it, you'll have it. Okay. Within few days as early as possible, so that everyone is oriented.
Is that 5 o'clock again?
Yeah. Did that suit all of you guys?
That worked for me.
Johnny?
Yeah.
Yeah.
I think shift, I think.
I think
Like
as far as I know,
4
Rob
PM.
also was fine with it. Notice I'm available all the way from 4 o'clock, 4 o'clock, or even a little earlier. So if you guys want, I can make it earlier, but that's okay. 5 is good for me. Yeah, just for you guys. And
Do you think the final will be in this room?
I think so.
Okay.
I think we should be okay. I like this semester, I hardly see it occupied. Usually I reserve these rooms and worry about it. But first thing is that I hardly see it used, getting it used. And second is we are only 3 people. In the worst case, in the very worst case, like students' lounge is also possible, or in the corridor. You sit it in the corridor. I feel less worried about it. Yeah. So. Okay, so we wanted to have, like we did, construct the point array matrix if you want. And we said, we were talking about Stone-Gerlach experiment. So let's get back to that. And actually, before that, before I get into Stone-Gerlach experiment, I want to give some vector space properties. So vector space and quantum mechanics. I want to say this before so that you can, and often the notations kind of you get carried away with the notations, and there is this like the overwhelming feature there. So we have studied vectors in the first part of this course, so I want to use those concepts and try to tell something which is very generic, doesn't have to be a very particular experiment. So let's have a basis, and let's say this is E1 hat and E1 hat, right? Is that a scalar, a vector, or a matrix?
Tensor.
It's a tensor, right? So it's a matrix, or yeah, tensor, that's the right word. So it is a tensor because it's not dotted. If there was a dot product in there, then you would say it's a scalar. If there is a cross product in there, then you will say it's a vector. If there is nothing, usually you write a circle with a cross there, that's a tensor product, or the way I write it is that I just don't write anything in it. It's understood that it's a tensor. Okay. So that's a tensor. And if there are two eigenstates, you can say E1 plus E2, E2, and this is equal to 1. If there are only two, if it's a two-dimensional system, this is an identity tensor. The same space, let us say, is spanned by another basis set, which is 2. Is that clear? I mean, what I mean by that is just two unit vectors of the same space, two independent unit vectors of the same space. And since they are a complete set, they satisfy this relation. There is nothing more than that any vector can be decomposed into these unit vectors. Now we want to talk about a series a series of measurement, if you can say, if you want to talk about quantum mechanics. Let's say we have a vector, any vector, and we take its E1 component. Okay. We select the E1 component. There is. We select the E1 component out of any vector that was available. In there, we take that component, and now I have a, you can say, a device that can either measure E1, which I will say if I can either select E1 or E2. Okay. So think of, we talked about Stern-Gerlach, right? You can select an up or a down or spin. So that's something like that, right? So if it is E1, and if I were to, I can select this or this, right? That means that I'm selecting something. So I'm going to select this and drop everything else. Like I'm going to stop that point in this, right? Which means that, okay, E1 will come to this and still it is E1, right? So nothing happens, it just goes through, right? So there is nothing special in there. Now let's say there is another apparatus here, which is designed to select G1 and G2. Again, I have a choice of selecting one or G1 or selecting G2, or actually I can select both, right? That's perfectly fine. But what I will do is that I will select G1, but not select G2. Okay, so basically you block that, right? So there is a beam that gets deflected a little. I'll just put a small cover it in a sense, right? And then I again come back, and there is another apparatus here, which can again do, so this I can repeat it as many times as I want. My setup is going to involve these three. And this time again, I select this one, E1, right? Now we have selected this. And eventually, so now this is all apparatus. Now at the very final end, I want to see whether this is one or the other. So I will say is what is the probability of getting E1? That's my question. So I start from E1. What is the probability that I get back E1? I can also ask what is the probability that I can get back E2. That's also perfectly fine, but this is my setup kind of, right? So I have an apparatus, I do something, it goes at E1 and E2, I can select and so on. Any questions on the construction? Right. I guess as far as the explanation of this system goes. Okay, so here now I will talk about probability amplitude, right? So this is getting yes. Okay. So now I have to talk about probability amplitude for this. Which I will just call A. And that's going to be equal to, I start with E1, so I start with E1. E1. The next one, this has to be projected onto E1. Remember, whenever I have a vector, if I want to project it in a basis vector, I'll multiply it with I hat, right? So I dot it with that, so I dot product with that. Let's dot with E1, E1. And that's because I selected this. This can be interpreted as this is killing E1, so it's projecting on E1, and then this is creating E1 in the sense. So it's killing, and so that's an interpretation one can have. But this is basically a dot product here. Then I take a dot product with the G1. And then I take a dot product with 1. And eventually, I want to collapse it. I'm saying I'm interested only in E1. That's E1. Okay. Is that very clear? Any questions? Okay. And next is probability. So next is probability, right? So probability. Equal to P. It is magnitude. This could be a complex quantity. So I will take a magnitude. Okay. Now, I want to contrast this with, so this is going to be what we will do in Stern-Gerlach setup also. But to get the counterintuitive feature here, what I want to contrast this with is that I have this, but I'll do the same thing again. E1 hat. Everything same. G1. And again, E1, right? I select. So now again, I have to decide what am I selecting here. So I do the same thing. I select the first one. And at the end one also, I select the first one. In the second one, I of course have the possibility that I can close this and select this. That's pretty similar to that. But what I'm going to do next is I select both. Okay. And let me call this A1, right? Let's call this P1. And let's call this A2. Okay. Sorry, not A2, right? So that is a A1 or A2, right? There is a corresponding thing for A2 also. A2 will be this close, this Is that clear what I mean? I kind of like the same system. If I close the top one, that's what I mean by A2. I'm not having space. I don't want to, I'm being lazy there. Right? Is that clear? So that's A2. And this one, we'll call it A1 plus 2. Now, simplistically speaking, one would think that if this probability is something, this probability is something, we should have something additional, right? Like superposition, something. But the interesting feature is that if you were to let both together, right, nothing will happen. Like this is what we mean by saying that a measurement disturbs the system. If I select this, it gets disturbed. If I select this, it gets disturbed. But here I'm not selecting anything. So basically I'm not measuring. So the system will not do anything. System will go through as if this was not there. Okay. So let's see the algebra, what is happening. So let's go slow. Okay. I think I'm jumping. Okay. So let's do this properly. So let me do this as first. Is that it? So this is A2 now. Let's go slow. I think this is A2. This will be E1. E1, E1, E2, 2. Okay, so let's, and the third one, is that clear? Oh, very clear. Third one I want to do is this is right. So this is E1, E1. So this is being selected, but in this case, G1, G1. This both are selected, right? That's a difference. Which should I select? So let's say this is A1 plus 2. So this will be equal to, now there's two of them, right? So how do you do this? So there are two pieces. So this will be E1. After this, E1, E1. So this is slightly new way, right? Now there are two. I have opened both of them. This will be equal to this plus this. So some piece there. So it's like a vector, right? Two components. So this is G1, G1 plus G2. Got it. Is that clear? Yes.
So, excuse me, so the E1 tensors, they don't get added to each other, I guess. Like it's not like
E1 doesn't get added means?
yeah, like the A1 and A2, they don't add their.
Oh, it's not that I added these two. Like I'm saying, what is the system doing? Here there was E1, it collapsed into E1, and there is an E1, there's a new vector. Now it's a matter of experiment decides, do I collapse it into G1 or G2? But the experiment has designed that I'm going to select both. If yes, I'll ask, have you collapsed into G1? Yes. Have you collapsed into G2? Oh, either one. Okay, so almost everyone will go through,
Okay.
right? So this is a selection I'm making. So the word is selection here versus not selecting.
So yeah, so the probability of getting both of them is one. Like just
Exactly. That's the point. That's a key here, right? So
Okay.
this piece is one,
okay. I see.
right?
Mhm.
So even though this is going through the system, it doesn't matter because this is actually one. Like that is the key. That's what I'm trying to point out here. That's what I'm building up, is that this is one. The very next step, you would say that, oh, this is E1 dotted with E1 dotted with E1. That's one. Dotted with E1, E1 dotted with E1. Correct. This is one. This is one. That's one. This is one. Overall, this is one. Correct. It's the same system. I mean, if I just stopped it, correct? I didn't do much. So this is very counterintuitive. You don't expect this to happen. Like what you're trying to say is that if I look into the system behaves differently. So let's go back and calculate A1, right? At this stage, when this is one, it is interesting to ask what is A1? A1 is E1 dotted with E1 and E1 dotted with G1 and G1 dotted with E1 and then E1 dotted with E1. This is again one. That's again one. This is not probability, by the way. This is a probability amplitude. So this implies that E1, 2, E1 plus 2 is also equal to 1. So this one is E1 dotted with G1, and then you square it. Which means that if you want the probability, P1, this will be equal to magnitude of E1 dotted with E1 square. It could be a complex number, and then you square it again. A2 similarly equal to you do the same story, right? This is U2. Again, those are one, so this is E1 dotted with G2 square. And then you have to square this, right? So this is P2 equal to P1 P2 square, the whole square of. And clearly, this need not be zero. Of course, you can select your vectors properly that this can be zero, but in general, this will not be zero, right? And but if you do not select it, like this, like see the words I'm using, if you do not select it, the system doesn't do anything, right? So that's the point I want to. So this is the, you can say, math behind what we'll talk about in Stern-Gerlach experiment. Because I'll change the whole notation. We won't use E1, E2. Now you'll use sigma matrices and the Bryan-Ket notation, but idea will be exactly the same. Words will exactly be the same. And let's have a proceed. Okay, any questions at this stage? Okay, so let's say Stern-Gerlach experiment. All right, so Stern-Gerlach. So here we have a silver atoms, right? They come and you collimate them, silver atoms come, you basically heat a lot of silver atoms, each silver atom has a spin, and you put it in a magnetic field. Okay, so that's your north pole, that's your south pole. And you have a choice to pick your magnetic field in a particular direction, right? So let's first select, this will be Z hat. Right, so the first magnetic field I put these atoms is going to be in the Z hat direction. Is that clear? This is a magnetic field in the Z hat direction. Okay, so this is a north pole and a south pole. I write the direction of that in the Z hat. In general, it could be any angle theta phi, but I'm going to make it simple like this. Just have X, and I'll talk about only terms of X, Y, Z, but if it was a complete quantum mechanics course, we can talk about the whole theta phi here. Let's just stick to Z and X. Let's say. The second one, I say this is in the X hat direction. Again, that's a north pole, upward direction. Now I have a choice. This again splits, right? This beam gets deflected. It gets into two pieces. I select this and stop this. Okay. And the same thing here. I select this. I stop this. And the third piece, I select again Z hat. And we can construct a lot of such experiments. All combinations are possible, but I'm just going to do this. And now we have to begin with, what did we start with? Let's say in general here, this is all actually, I should be a little, let me do one more. Actually, it doesn't matter. Yeah, so this is, no, I want to be able to, I want to input, right? So I will put one more in front in the Z hat direction, because I want to put that E1 inside, right? So I select this first and then put it in. But that apparatus is going to be shown as this apparatus. Don't want to show it as an apparatus. The beam itself is polarized. Think of it as a polarized beam. So it's a positive 0 Z hat direction. Okay, is that clear? So instead of E1 now, I'll call it the branch. So let me come back to that. That's not very clear yet. What is the system that does this job? That's a Hamiltonian, H, and Hamiltonian is minus magnetic moment dotted with the magnetic field, right? The energy of all these spins is decided by, or is characterized by, the magnetic moment, and the magnetic field is the interaction with this. Each apparatus obeys this, or is described by this Hamiltonian. What is this Hamiltonian? The M here, M magnetic moment is Q over 2M, right, times angular momentum. Angular momentum, we say, in this case, is H bar over 2 times sigma matrix. So that's the same as, so Q times, that is a magnetic field B, and B itself, I say, is magnetic field is equal to B times R hat. It's in the radial direction, and we said that there is a slight issue there because magnetic field cannot be radial, right? It has to be divergence-less. So this is not a realistic magnetic field. So with that caveat in there, let's keep going. So this comes out to be minus H naught times sigma dot with R hat, right? Where H naught is equal to Q B over M, right? So let me say H bar over 2 times omega, right? So that is so 1 by 2 times QB over M. QB over M is what? What is that? There is a special name for that?
Velocity.
Velocity? Yeah,
Mm.
angular velocity.
Frequency.
Yeah, frequency. What is it called? Which frequency? Yeah, that's correct. Frequency.
Gyration.
No. If you put it in a magnetic field, a charge goes in a circle. Cyclotron frequency, right? So this is, if you put it in a magnetic field, a charge, and the frequency, that's the cyclotron frequency. So H cut omega, that's energy, right? That's so in that sense, that energy. We will like to write this as H naught and sigma, just a sigma. Notice this is a sigma vector. When I dot it with R hat, it becomes a scalar, but it's a matrix. So it will depend on theta phi. I'll write it like this, okay? Where sigma theta phi now, sigma theta phi is equal to sigma dotted with R hat. Let's move that forward. It's equal to cosine theta. Sine theta equals to I phi. Sine theta. I phi and minus cosine theta. Okay, that's the matrix, right? So this Hamiltonian is not a scalar, or it is a scalar, but it's a scalar in the sense that it is a matrix also, right? Typically, it's not a number. I think that's a point. So then the question comes: what happens when we measure it, right? So what is actually the measurement do? And that's where our collapse, the interpretation that comes in. So immediately we say, oh, this has two eigenvalues, right? So it is plus or minus 1. And eigenvalues are plus or minus 1, let me say. That's clear, we have done that before. And we will label the, denote the eigenvectors as theta phi equal to, there is some sine theta over 2, sine theta over 2 equals to minus pi by 2. Minus theta equal to e raised to pi alpha 2 minus sine. So this is the already. So I'm going to use a new notation now because we're confining ourselves to z and x. We will say z hat, right? Means theta is equal to 0 and phi equal to 0. So this is going to be plus 0, 0. That's equal to 0 is 1, 0. And let me choose alpha 1 equal to 0. So this is 1, 0. Let me say minus of z hat equal to minus of 0, 0. That's equal to minus is here, right? So cosine is in the denominator, so that's 0, 1. That's eigenvalues of, eigenvectors of sigma z matrix, right? Polymatrix, the third polymatrix. Any questions?
Yes. You said those were the eigenvalues?
These are the eigenvectors of sigma z.
Okay.
Sigma z, if you recall, sigma z is nothing but theta phi. This is exactly like In general, you can talk about now sigma z when it is in some arbitrary direction, and that's perfectly okay. There'll be angle theta and phi showing up. So now we are going to restrict ourselves to only z and x, right? So this becomes plus pi by 2 and 0. What is that equal to? Without the phase, let's say that the phase equal. What is that equal to?
Eigenvectors.
Eigenvector of x, how much is that number? Can you guys calculate for me?
1001.
No?
So
1001, because that's that here, right? Substitute theta equal to pi by 2 and phi equal to 0 in this.
-1.
Minus 1 and 0? This one? No? This is plus. So
Oh,
we
yeah,
have to
so
go here.
this one. Okay.
Yeah.
So it equal to 45 degree. 1 by 2, 1 by 2. 1 by root 2.
1 by root 2, 1 by root 2, right? Good. Right. So 1 by root 2, 1 by root 2. So good. Right. And what about minus? Second eigenvector?
Yes.
Same?
Yeah, minus 1 by root 2.
Oh, yeah, minus, right? Because it's minus.
Yeah.
Good. It's minus 1 over root 2. Good. Okay. So now we have all the things available for us. Okay, clear?
Why don't we need the y?
Oh, we do. Okay, in general, we need everything. Right? But I said I'm going to confine my analysis to z, x, and z.
I see.
Right? I can have anything I want here, not even x, y, and z. I can make it 45 degrees. Right? And I have a matrix here. This is a very general system. And in an experiment, you can actually do this. Right? You get a beam. I first set z. Next one, I can put 30 degrees. Why 45 degrees? 30, I can put 10.78 degrees. Perfectly fine. So you have the ability to do all that, but this is, I am compressing the whole quantum mechanics into 2 lectures, 3 lectures. So let's, and this gives you the idea, at least one piece, one statement. My only point here is that one non-trivial statement about quantum mechanics is that measurement disturbs the system. And that's what I'm trying to illustrate here as to what we mean by saying measurement disturbs the system. And it has to be complementary variables. These are all languages that we use. Like the z and x, in a sense, I'm choosing very special ones in the sense that, so here, this is another language. If I select z and afterwards select z, x, and z and x are complementary, like x and p are complementary, they obey Heisenberg uncertainty relation. The measurement of x will erase the memory of z. After that, when I measure it, it doesn't know whether this existed or not. It could have been a random event coming in. I measure x hat and I get that. And this, same thing. So basically a complementary variable measurement in series, one gets rid of the other in the complete sense, as much as possible. Usually, like at least in this case, it's complete, but there is a maximum possible. It will take it to the maximum limit. The maximum, like there is a less than or equal to h by 2, right? Like the error in x and uncertainty relation has this greater than or equal to h by 2. So here it becomes really the equal sign. Like this is the minimal you can get. You cannot get more than that. Right? So the extreme version is carried out if it's a complementary variable. So in that sense, z and x is a good choice. If I take a 10 degree, 30 degrees, it is not true. In Stone-Galak experiment. But those are details. Let's not worry about that, right? So I'm again trying to get only the measurable measurement point. Okay. So now that we have the setup, let's go back and do this, but now in this language. Only the language changes, otherwise E1, E2, keep that in mind, right? But that's exactly what I'm going to do, but now in the bracket notation. Okay. So it's same vector space. So again, I'll draw it just for completeness. Let me say so that is a plus, so plus Z hat, right? And that is a minus Z hat, right? So I can select atoms that are aligned with the magnetic field in the Z hat or bottom, or I can have plus X hat and minus X hat. And this should be actually this one, right? A perfect thing. So that's the projection operator. Is that clear what I mean? I'm being lazy again. Let me write it. No confusion. That's not. Okay. And to begin with, I need to have something I'm measuring things with, right? In the beginning, what is my beam? And I say that my beam is a polarized beam if you want. And that's in the Z hat. Again, this need not be in the Z and X at all, right? But it's a very special choice I'm making. And at the end, let's say again, want to look for that part of the beam which is aligned with the plus Z. So this selection itself involves an apparatus. This itself involves an apparatus, but that's okay. So the amplitude now, or amplitude will be equal to, I should actually be careful, since it's the first one, we have to actually put it like this. This has to collapse with that, right? Reverse sign. Like when we were doing E1, it was a real quantity, so we didn't worry too much. Okay, so this one now will be plus X. So this time I'll place it in brackets or parentheses, but the idea should be clear. That's clear.
Why did you use the opposite sign into that? Up.
This one?
Left.
Oh, because it's the first one, right? So I have to set some rule. The first one will be, okay, so what is happening here is that I said that this is an apparatus, right? There is a beam coming in, this destroys that, and this creates that, right? In the first beam, whatever, this is a source, so source creates the right side product, right? This is projected into that, and that is created. So it's a two-stage process. Like I think that's the way to look at it in quantum mechanics, that it is not happening as a continuous process. Whatever is coming, you first make it collapse, and then you create the new. It's a two-stage process. Did that answer?
Yeah. Thank you. Can I do the work?
Sure, sure, sure. Any questions here? Okay, so now basically we just have put in numbers, right? So let's plug in all the numbers, right? We know these vectors. So this is 1, 0. This is a row matrix because whenever it's a bra, it's a row, and the cat it's a column, right? So this is 1, 0, and then this is 1, 0. Then this is again 1, 0. So these two together is a number, right? These two together is a matrix if you want, right? So this is 1, 0, and so this is 1, 0. So this is this, and now this is plus 1 over this 2. And then again 1, 0, 1, 0, 1, 0. Forward. Overall, it's a number. Is that clear? There are various ways of looking at this. You can think of this as a number, right? 4 numbers getting multiplied. Or you can also look at this as, so this you can say is 1. Or first let me write the other one. So this is 1, 0. This is 1, 0, 0, 0. And this is 1 over root 2, 1. So it's 1 over 2, 1 over 2, 1 over 2. 2. And it is 1, 0, 0, 0. This way has this nice interpretation that each matrix corresponds to an apparatus. Right? And this is your initial vector, initial polarization, that's a final polarization, and you're collapsing it in that. That's one interpretation. But you can also see the way I was telling earlier. You project this into this, this into this. So that's a projection way of looking at it. But let's see this. So this is equal to 1. This is 1. So this is 1, 0, right? So that's 1. So this is 1, 0, and 1 by 2, 1 by 2, 1 by 2, 1 by 2. So that's the same as how much? 1 by 2 and 1 by 2. So this is 1 by 2. Overall, it's 1 by 2. Space there. That's 1 by 2. Which implies that the probability is. Oh, did I get this right? Yeah, probability is 1 by 4. Yeah, that's correct. 1 by 4. So the idea is to see the probability is that there is 1, the total probability here is 1, distributes into 2, because this is already 1, this will be 1, 2, right here. This distributes into 2, right? 1 by 2, 1 by 2, and this is again 1 by, so that will be 1 by 4. But that is assuming these are complementary variables. In general, it doesn't have to be, it is on cosine theta. But the total will always add up to 1. Right? The total probability also always has to happen. Again, we won't go into all those details, but all those has to be verified at some arbitrary angle. It's not very obvious. Is it really going to be 1? But that's somewhere else we do that. Okay, so this any questions here at this point? Yes.
So A is probability amplitude.
Correct.
And P is the probability.
Probability.
So which one can we, explain?
Measure P,
Yeah.
probability. This is off by a phase. Right? So this is where that if you were to put this I alpha 1 and all that,
Mhm.
here that content will be there. But the moment you square it, the phase will become.
Mhm.
So that's like this is not observable. Like this is what we observed.
Okay. So what is the physical significance of A then, the value of A?
Oh, um, I don't know. Okay, but I can give you an analogy.
Mhm.
Okay. In interference, you have a amplitude of the electric field,
Mhm.
correct? And then the intensity is squared,
Yeah.
right? So this is the amplitude, that electric field is this quantity. But there it is different in the sense electric field can be measured. Right? So square is what we are interested in, intensity, that's different. But in quantum mechanics, psi cannot be measured. Yeah, the wave function cannot be measured. But wave function square has this information that it is it's a physical quantity. So in that sense, I don't know what wave function is. In that sense, I don't know. But there is this interesting features. So now you say that okay, especially in the phase of anything that from here to here you lose a lot of information. Correct? So there is an arbitrariness. Correct? And that is the same arbitrariness that you see in electromagnetism. Del cross A is equal to B, right? The vector potential, there is a lot of arbitrariness. We cannot measure vector potential. Is that clear what I mean?
Yeah.
So that's very similar. And that shows up into the, you would say that, oh, that is electromagnetism, this is electrons. Actually, these two are connected. So the A leads to the wave function phase. Okay, whatever A is, it will show up as in the phase of an electron because electrons and photons are connected, remember, using quantum electrodynamics. They are two faces of the same coin. Right? In that sense, it is there. So, but let me, it's better for me to answer your question as I don't know. Okay. Or you should think about it, or you should study about it. Okay. It is a lot more deep. It's a deeper question. It has a lot of rich answer in it. Okay.
Is it anything to do with quantum error correction nowadays? I mean, scientists are working on
that. I really don't, because I really don't work on it, and those are all very recent things that is there. That I really don't know. The other one I'm trying to avoid telling. I'm trying to.
So this probability is 25% possibility that, I mean, if somebody write it in language, English language, what is the meaning?
That's 25%. So if the main thing is if there were million atoms that came in here, 250,000 will be out there. You'll be able to see only quarter. That. And they're really big in number, right? Like when you talk about a gas of atom, even if it is pressure is reduced by 10 raised to -7, even then there are 10 raised to 15 atoms. Like 1 cubic centimeter has 10 raised to 23 atoms. So even if the pressure gets down by 1,000,000, or usually these days even nano bars are possible, but you still have a lot of, like, that's the best vacuum we can talk about, right? And still there are lots of atoms. So statistically, this is great. Right? Whenever you're talking about atoms, statistically, you're wonderful. Right? So in that sense, it's a pretty, when we say that this is probably pretty much works, that's why quantum mechanics works in atomic systems.
Thank you.
Yeah. Question? Yeah. Okay. So that's P is equal to 1/4. Now we do the same thing there, right? I mean, what if I select, oh, I didn't mark this, right? So I was supposed to say that this I select this, and I select this. Right? And the next one, I select the opposite, and then I put it together. So the second one is again, I say plus z hat. And if you allow me, I'll just write z hat here, right? So this time, that's the magnet in the z hat direction. I select this. And in the second one, maybe I can draw it like this. So this is the magnet here. So this is z hat. So that's your x hat. And this time I select the bottom one. It's just being lazy. And I messed up again, right? I should have said from this. And the probability amplitude is clear. Let me call this A2 this time. So this is plus z hat plus you hat. Keep going, right? This time it is minus, right? I'm selecting the minus x hat. Okay. This is one. This time I'll do it in this way. Earlier I put in the matrices, slightly doing it in a different way. That's equal to 1. So that's equal to, this is plus hat. So this is 1, 0. And this is 1 over root 2. No, minus 1 over root 2, right? Minus x hat, which is minus 1 over root 2, 1 over root 2. Minus 1 over root 2 times 1, 0. So this is minus 1 over root 2. The number, right? Minus 1 over root 2. And this is also minus 1 over root 2. 1 by 2. And P2 then, 1 by 4. Okay.
Yeah.
And then one would, naively think, again, this is, once you're familiar with interference and all, this shouldn't be too surprising. But at the same time, this is slightly different in the sense that here, actually the system is going through. The only thing you did is that you took out a cap there. Like that's what, often you say double slit experiment. Did I look through this or not? If I close this, it does something. If I open this, it does something else. That's exactly what we are looking for. Now let's say the third one. This is the counterintuitive one. And that's that you do z hat. Right? And in the x hat direction, you allow both. And rest everything you keep it as it is. And let me call this A1 plus 2. And again, this will be plus z hat. This will be plus z hat. that is, and this time, yeah, okay. Right. And now this one is the important piece. There is two of them now. So there's plus x hat plus x hat. Then this is a plus, that's not a plus. This is an actual plus, not the plus for the vector. And this is minus x hat minus x hat. Clear? And let me space. And this is plus b hat plus hat. And then plus. And even like I can of course put in the numbers and see, I mean, if you want to, I mean, you can actually calculate the amplitude, it'll be all the same. But even before you to calculate that, you say, oh, this is not going to do anything because this is equal to 1. This is completeness relation. So this is equal to 1. And that is equivalent to saying that x hat doesn't do anything. Like even though it is the same experiment, the only thing, this is the thing about measurement, right? I mean, it seems like the system knows whether you looked into it or not, like you selected it or not. So that's the language you use. That's a surprising part. It's a non-trivial part. But when we look at it in terms of the vector space, is quantities, that's obvious. That is one, of course, that will happen. But if you're not familiar, see, this is what Heisenberg brought in, right? Heisenberg gave this interpretation. If this algebra was not there, if you remove this mathematics and see this experiment, how is this possible? I mean, when I'm looking into it, it seems to know that what I'm doing. That's not the idea, but the main idea is that a vector space has this property. And this is 1, so it's just 1. I don't know. I'm keep on posting. Yes. That's all. Stop it. Yes.
Earlier you said that if we were to choose 2 of them, the previous information kind of gets erased.
Yes.
I'm having a difficulty seeing that.
Okay, so yeah, let me clarify now that I have time, I can actually go through this. Right? So. Okay, so let's have this. So this is another statement of quantum mechanics that if you measure one, it erases the information of the other, right? It's like saying you measure position, you have lost the information about velocity, right? You have too much error on the velocity. You go back and select velocity, or you lost the information of x. So you cannot have simultaneous. That's a basic idea of quantum mechanics. So let's see what this is. Let's say that this is an unpolarized beam coming in. So this is unpolarized. Completely unpolarized. That means it's truly random. Right? And now I select my plus z, right? So this is plus z and minus z. Minus z. And I do this. I select this. And okay, what will be the probability now? Like that's unpolarized completely. This will be exactly half, right? Half of them will go up, half of them will come down. There's nothing else that will happen. So if I were to select plus z hat, So that's probability is 1/2. And that's because it is unpolarized, right? Exactly half of them will collapse into that and half of them. Now let us say that I measure the x direction and then again do the plus direction. Okay? And if I get back my half, that means plus x did basically got rid of all my z. Okay, so that's what I'm going to do. So let me do the next one. So this is unpolarized now. Unpolarized. And again, let's do this plus z and minus z. And then plus x minus x. Right, and I select here, and I select here, right, I selected plus, and then I do this again. Right, so this is plus z hat. Okay. So what I'm doing is that by measuring in x, I'm erasing its ability to be in the z. Like the z will actually collapse equally in the x direction. That's one way of looking at it. One can see it as a cone when you look at it, but let me just do this. And then, then I am again doing just this, right? Plus z, and yeah, this one. Right. So I'm, no, I want to select this again, right? So if I select plus z again, so this is, yeah, this is okay. I think this is okay. Yeah, plus z and minus z. The only difference is that from earlier is that this is unpolarized, right? Earlier I had this plus z coming in. That is not available for me anymore. I can only say that this will be, so I will start from here with a complete beam here, right? So this begins with this. So that's the idea, because this will select the plus, that's all it is doing. Okay, so the probability or probability, that's right, will be the square of this, right? I have to make sure that I don't forget to square that. And so that's the square, right? And this one collapses with this, so this is plus hat plus x hat, and then plus x hat and plus z hat, right? Plus z hat, and there's one more plus z hat, plus z hat. That's all square. So the only thing with difference is that because it is unpolarized, I don't have that initial piece in there. Okay, so let's see how much this is. So this is is this not again 1/4? This is 1. So this collapses into 2. I am again making that collapse into 2, so I should ask my question correctly. Okay, unpolarized gets, you put a Stern-Gerlach apparatus, it gets into plus and minus. There is a probability of half and half, right? I measure x, so this is what I do. I measure x. So now I first measure z, so it gets selected into 2. Then measure x, I'm supposed to destroy that. Yeah, and not do this, right? I think I don't want to do this. Yeah, so the whole point is if I make a measurement of x, and if I get if it was an unpolarized beam, I should get a plus will be half and minus will be half. Right? That means it's unpolarized, completely destroys its ability. Correct? So this you again ask, what is the possibility of a plus x in here, and what is the possibility of a minus x in here? So you do 2 of them in there, and let's just go with that. If you know this is plus half, then you know that that is the rest of that, and that comes out to be exactly half. Let's see if that works or not. So this is plus z plus es. So this will be plus x, and this is squared. So this is 1. So this will be 1 over root 2 squared. So that will be 1 by 2. Did I clarify? Did that make that clear? Like this is 1 over root 2. Notice. Because 1, 0, 1 over root 2, 1 over root 2. Okay. So that's 1 over root 2.
And then the other one's 1 over 2.
This is 1, right?
This is one. Yeah.
This is 1. So let's make this clear. So 1, 0, 1 over 2. 1 over 2. That's equals 1 by 2. And same thing will happen with minus also. So what I'm trying to say is that, I mean, think again, the interpretation is that there is an unpolarized beam. You take a magnetic field and you should get equal half and half, right? Here there was an unpolarized beam. I polarized it, correct? And then I made another measurement in the x direction. And it again gave me 1/2, 1/2. That's like unpolarized. Whenever you get 1/2, 1/2, it is unpolarized, right? So the interpretation is that x, or the statement, what you say then is that x destroyed the measurement of, or the information about x. Like from this point on, you don't know whether the beam was here or here, right? Like the z information is gone completely. So that's this is popularized at the level that measurement destroys the earlier measurement. And that happens only with complementary variables. And the uncertainty, like x and t will do this, Lx and Ly will do this. But if I turn the magnetic field by 40 degrees, it won't do it. Like still there will be some information left. That, yeah, I think good question. I think we had some time, so we could go through it. So that was good, yeah. But I hopefully not did not confuse the stage. Yeah. Okay, good.
Thank you.
Yeah, yeah.